Most people think the internet is a cloud, a signal, something ambient that exists in the air around them, delivered invisibly to wherever they happen to be sitting. That belief is understandable. The experience was engineered to feel exactly that way. You tap something and it loads. You send something and it arrives. The infrastructure underneath is invisible until the moment it stops working. And even then, you assume something somewhere is being fixed by someone, and that normal will return before it matters. Here is what is actually underneath that experience. More than 95% of international data and voice transfers, every international call, every cross-border payment, every video you have ever streamed from a foreign server moves through physical cables lying on the ocean floor. Not satellites, not radio waves, cables. Fiber optic lines running through the dark at the bottom of the sea, some of them no thicker than a garden hose. As of early 2025, there were 570 of those cable systems in service globally. 81 more were planned. The total length of cable currently on the seafloor was approximately 1.48 million kilometers. The internet is not weightless. It is one of the largest physical machine human beings have ever assembled. It runs under oceans, along railroad corridors, beneath roads, through anonymous industrial buildings, in places you have driven past your entire life without once asking what was inside. And almost everything in modern American life now assumes this machine will always be there. Your paycheck, your navigation, your medical records, your group texts, your work login, your bank transfer, your 911 call. So the question is not how the internet works. The real question is who keeps it alive and what actually happens when they cannot. I am Marcus. Let's get into it. Start with a morning, not a dramatic one. Alarm goes off. You check your phone. You log into something for work. You look up a route. You send a message. You approve a payment. Someone checks a school portal. You verify a two-factor authentication code on an app that sends you a text. Every one of those actions, before it becomes anything you experience, travels a physical route. It leaves your device, moves through the connection into your building, passes into a regional network, crosses into a high-capacity backbone, reaches an exchange point, traverses long-haul fiber, and eventually passes through a cable system, possibly buried underground, possibly sitting on the floor of the Atlantic Ocean, before arriving at whatever server was waiting for it. Then the response travels the same path in reverse. All of that happens in under a second, which is precisely why you have never had any reason to think about it. You have interacted with this system thousands of times. You just were never introduced to it. The physical endpoints of this system have actual addresses. The United States had 96 active submarine cable systems landing on its shores as of 2025. Those cables come ashore at specific buildings on specific coastlines, buildings that look, from the outside, like nothing in particular. And from there, they feed into terrestrial fiber networks running underground across the country. Those networks do not connect at random. They meet at specific facilities called internet exchange points, where separate networks hand traffic to each other and agree in real time where it should go next. The largest concentration of these facilities in the world is in Loudoun County, Virginia. Local estimates put the data center count in that region above 250 facilities. The Regional Commission describes it as processing roughly 70% of global internet traffic. 70% of global internet traffic moves through a county that most people outside the industry have never had cause to consider. That is not a point of regional pride. It is a fact about geographic concentration that has been accumulating quietly for 2 decades. The internet is not one thing owned by one entity. It is thousands of separate networks run by telecommunications companies, cloud providers, universities, governments, and corporations that have agreed to exchange traffic with each other. Those agreements take 2 main forms. The first is called transit. One network pays another to carry its traffic farther than it can reach on its own. The second is called peering. 2 networks exchange traffic directly, for free, because both benefit from the shortcut. Peering reduces the number of intermediaries, lowers cost, and shortens the path traffic has to travel. More than 99% of peering relationships in the world are settlement-free, meaning they run on mutual interest and informal agreement, not contracts, not payment. Research by the European body that regulates electronic communications found that 99.93% of peering arrangements globally were informal handshake deals, no written contract. So the foundational layer of the global internet is held together primarily by reciprocal trust between networks that have decided cooperation is cheaper than the alternative. That is not a weakness. It is also not what most people would guess if you ask them how the internet stays up. The answer people reach for is technology. The actual answer, in large part, is norms. Behind those norms is labor. There are people whose job it is to watch traffic move across networks in real time, around the clock, from operation centers that look like something between an airport control tower and a very quiet casino. They are called Network Operations Center engineers. They are the first line of detection when something starts to go wrong. There are fiber crews that drive out to wherever a physical cable was damaged by construction equipment, by weather, by an errant backhoe, and splice it back together. There are data center technicians managing servers, cooling systems, and power. There are operators monitoring the routing tables that tell traffic where it should go. And there is a category of worker that most people have never thought about at all: the technicians who repair submarine cables. About 200 submarine cable repairs happen globally every year. Not in a bad year, every year. Cable damage is not a crisis, it is a constant. The system was designed with the explicit assumption that it would always be happening somewhere. 86% of those repairs are caused by fishing gear or anchors, not sophisticated attacks, not coordinated sabotage, boat equipment. The primary physical threat to the infrastructure carrying 95% of international internet traffic is a fishing vessel dragging something along the sea floor without knowing what is down there. The repair process involves specialized ships equipped to locate cables on the ocean floor, grapple them to the surface, cut out the damaged section, splice in a replacement length, and lower the cable back. The European Commission's Joint Research Center has noted that a shortage of available repair ships is a meaningful constraint on recovery time. Some outages take weeks or months to fully resolve because the right vessel was not close enough. This is the part of the story that rarely surfaces in any conversation about the internet. The person responsible for making your video load is, in a non-trivial number of cases, a maritime technician on a ship somewhere over the horizon. Most of the time, the system absorbs all of this without announcing it. Then there are the times it does not. In June 2019, a company called Allegheny Technologies, a steel manufacturer in Pennsylvania, briefly became a significant routing node for large portions of the global internet. What happened was this: a routing optimization service used by a small regional ISP generated a set of instructions that leaked to Verizon, which accepted them and propagated them outward. The result was that traffic intended for major networks, including Cloudflare and Amazon, was rerouted through infrastructure that had no capacity to handle it. Cloudflare described it as the equivalent of a navigation app directing an entire freeway through a neighborhood street. The neighborhood street, in this case, belonged to a steel company. That kind of error is called a route leak. It happens because the system the internet uses to direct traffic, called BGP, was designed in the 1980s for a small network built on trust, among a limited number of institutions that all knew each other. It was not designed for a network of billions of devices and thousands of competing commercial operators. The trust model survived. The scale changed around it. That gap has been producing incidents like this one for decades. That gap is not a technical accident that nobody noticed. It is the original architecture operating exactly as designed, in conditions the original design never anticipated. Then there is the October 4th, 2021 Meta outage. Meta's own engineering team said that configuration changes made to their backbone routers caused failures that cascaded internally and brought their services to a halt. What happened from the outside was that Facebook stopped announcing to the rest of the internet that it existed. Its addressing information disappeared from the global routing table. Servers that wanted to reach Facebook could not find it, not because it was overwhelmed, but because it had effectively removed itself from the map. Instagram, WhatsApp, and Facebook were unreachable for roughly 6 hours. one of the most technically resourced company on Earth, vanished from the internet for 6 hours because of a configuration change made by its own engineers to its own internal systems. And Meta's employees could not use the internal tools they needed to diagnose the problem because those tools ran on the same network that had just gone dark. Then go to March of 2024. 3 submarine cables serving the west coast of Africa were cut within a short period. The disruption began around 5 in the morning UTC. By the time it resolved, 13 countries had experienced degraded or near-total internet outages. Payment systems failed, remote work stopped, cloud services became unreachable. The Internet Society's report on the event made explicit what usually stays implicit. Countries with weaker local interconnection and fewer redundant paths suffered more. The regions with less infrastructure had no backup route for the traffic that could no longer take the primary one. The FCC has formally stated that when a major fiber line is cut, it can disrupt 911 services, along with broadband, transportation systems, and banking. That statement is not a hypothetical. It is in a government document. The FCC is also in the process of shifting emergency response infrastructure, 911 systems, onto IP-based networks. The internet is no longer adjacent to emergency services in America. It is becoming part of their core architecture. If you have ever had the sense that the system underneath everyday life is more fragile than the ease of using it would suggest, that suspicion is not misplaced. Now here is where you have to understand how the incentives got built in. The internet began as a research project funded by the United States government. The ARPANET sent its first host-to-host message in 1969. By 1983, it had standardized on the protocols that still carry traffic today. By 1985, the National Science Foundation had built a backbone, NSF-NET, that connected universities and research institutions across the country. That backbone was public infrastructure, funded by the government, operated in the public interest, with an acceptable use policy that explicitly prohibited commercial traffic. In April of 1995, the NSF shut it down. The commercial internet took over, and the logic changed. Before 1995, the question driving infrastructure decisions was, what does this network need to be useful to the research community? After 1995, the question became, what does this network need to generate a return? That shift does not mean the internet got worse. It expanded dramatically, got faster, became accessible to hundreds of millions of people who would never have used a research network. But the people making decisions about what gets built and how resilient it is were now primarily making those decisions based on investment returns, not on what the public would need the system to do under pressure. The Netflix-Comcast dispute in 2014 made the downstream consequences of this briefly visible. Netflix was paying a transit provider to carry its traffic toward Comcast's customers. The interconnection point between that transit provider and Comcast was congested. Comcast was willing to relieve the congestion for a direct payment from Netflix. Netflix eventually paid. What users saw was buffering. What was actually happening was a negotiation over who absorbs the cost of carrying enormous traffic volumes, a negotiation that the market structure of the internet had made entirely predictable and entirely legal. That logic has continued to develop. An expert group convened by the European Union in 2025 found that the major technology platforms, Google, Meta, Microsoft, Amazon, had come to own approximately 90% of total capacity on the submarine cable route connecting the United States and Europe. 90%. I want to be precise about this because I checked it twice and I want you to understand what it describes. That is not 90% of one cable. That is 90% of total capacity on the most important submarine route in the world, which means the decisions about how resilient that route is, how much redundancy it has, where additional capacity gets built, those decisions are being made primarily by companies whose primary obligation is to carry their own traffic efficiently, not to serve as public communications infrastructure. Telegeography projects that the value of new submarine cables entering service between 2025 and 2027 will exceed $13 billion. The majority of that investment is coming from the same handful of companies that already dominate existing capacity. This is not a conspiracy. It is a market structure producing a predictable outcome. But the result is that decisions shaping the resilience of global internet infrastructure, which routes get built, which regions get served, how much redundancy exists when the primary path fails, are being made by actors whose interests and the public's interests are not always the same thing. The FCC moved in 2025 to update its rules around submarine cable landing licenses, citing evolving national security and foreign policy concerns. That action is the regulatory acknowledgement that private ownership of public dependency infrastructure has reached a concentration that warrants oversight. That is the government in writing saying this arrangement needs to be reconsidered. This is the same structural pattern I covered in the video on why apartment buildings all look the same, and the one on parking lot design. A system that functions as a public necessity gets optimized by private incentive, and the costs of that optimization fall on the people with the least leverage over how the system was built. What is different here is that you cannot see the substrate, so the optimization is almost completely invisible until the system fails. Private decisions, public consequences, no announcement. Here is where I want to leave you. The internet is impressive. The fact that it survives 200 cable repairs a year, route leaks originating from steel companies, self-inflicted outages by some of the wealthiest technology companies in history, and the drag of every fishing vessel in the North Sea while still delivering a response in under a second is genuinely remarkable engineering. That resilience is real, but it is not automatic, and it is not guaranteed, and it does not maintain itself. It survives because engineers in operations centers are watching it right now, because repair ships are staged and in transit, because decades of network operators built peering relationships with competitors on the logic that cooperation is more reliable than isolation, because there are people who splice fiber in places you will never visit and would not be able to find on a map. And it survives in its current form because the incentive structures that have shaped it over 3 decades of commercial operation happen to produce enough redundancy to keep the failure rate below the level that triggers sustained public attention. Engineers are in the process right now of retrofitting a cryptographic security layer onto the core routing system, work designed to prevent exactly the kind of route leak incidents that have been happening since the 1980s, because the original trust model was built for a network that no longer exists. That work is ongoing in 2026. 30 years after the problem was understood, the system is still being hardened. The hardening is not finished. The internet is not above American life. It is buried underneath it, running through the dark at the bottom of the ocean, through anonymous buildings on coastlines, through conduits beneath roads you drive on without thinking about what is inside them. The next time a page loads instantly, or a payment clears in a second, or a call connects before you have finished thinking about it, someone did something physical to make that possible. A routing decision, a splice, a repair, a handshake between 2 networks that calculated they were better off cooperating. You did not know their names before this video. You will not know them after. But now you know the machine is there, and you will start to see the edges of it, the nondescript buildings near the shore, the fiber warning signs along the highway, the unremarkable warehouses in the middle of Virginia that somehow carry the weight of the internet. It was always there. You just did not have a frame for it. If this video changed the way you picture the system underneath daily life, I want to hear what landed harder. Drop it in the comments. Genuinely, I read them, and the specifics help me figure out what to cover next. If you are not subscribed yet, now is a reasonable moment. Every video on this channel is about something you depend on every day without knowing why it is built the way it is. There is more to cover.